everyone, welcome again to Passnownow's WAEC preparatory class. In our last chemistry class, we analyzed questions that had to do with organic chemistry and mass and volume relationships. Today, we are still going to look at more problematic questions. And for today's class, we'll be starting with past question year 2019. Question number 1H. The question reads, consider the reaction represented by the following equation between hydrogen sulfide and sulfur 4 oxide to yield sulfur and water. I. State the species that is undergoing oxidation and the oxidizing agent. How do we determine the element or compound that is undergoing oxidation? From our definition of redox reaction, we know that reduction in terms of the removal of oxygen has to do with the loss of oxygen, while oxidation has to do with the gain of oxygen. Now, hydrogen sulfide here has lost sulfur to gain oxygen, and sulfur 4 oxide has lost oxygen to turn to sulfur. Hence, the element undergoing oxidation here is hydrogen sulfide. The next question says to state the oxidizing agent. Normally, we know that the element or agent that is undergoing reduction is the oxidizing agent. Hence, our oxidizing agent here is sulfur 4 oxide. Our next question asks, what is meant by carbon 12 scale? The carbon 12 scale is a scale. The carbon 12 scale is a scale that uses the carbon 12 isotope as a standard for comparing or measuring the atomic masses of other elements. I hope you understand. Now let's go to the next question. Our next question is taken from the same year 2019, question 2D. The question reads, element J has the following electron configuration of 1s, 2s, 2p6, 3s2. I. How many unpaired electrons can be found in J? II states whether J would be a good oxidizing or reducing agent. III states a reason for the answer in 2dii. Now, how do we determine the number of paired electrons? According to Horn's rule, we have to fill each orbital singly before we pair them up. Now, for 1s, for the element J, one has only one orbital, so we fill it singly. It takes 2, S block always takes 2 electrons. (2s) is also 1. 2s also takes 2 electrons. 2p has 3 suborbitals, which is 2px, 2px, 2py, and 2pz. And p block takes 6 electrons. We'll first fill it singly before we pair them up. Now, 3s, S block takes 2 electrons. From this, we can tell that there is no unpaired electrons because each orbital has been paired up perfectly. So the answer to that question is that J has no unpaired electrons. The IR part asks us if The II section asks if J will be a good reducing or a good oxidizing agent. Now, from my analysis, I can tell that J will be a good reducing agent. I know you're asking how. Well, that is the question that the next question, which is III, asks. Now, how can we determine if J is actually a good reducing agent? We can see here that J belongs to the 3S block. And elements in the S block are seen or are known to be good reducing agents because they can easily lose the 2 electrons to become stable. Hence, J, according to III, is a good reducing agent. Do you understand? Now, let's go to our next question. Our next question will be taken from year 2018, question 1C. The question reads, consider the following reaction equation, iron Fe plus hydrogen tetraisosulfate 6 to yield iron tetraisosulfate 6 and hydrogen gas. Calculate the mass of unreacted iron when 5.0 grams of iron reacts with 10 centimeter cube of 1.0 mole per dm cube of hydrogen tetraisosulfate 6. And we are given the molar mass or relative atomic mass of iron as 56. Now, what exactly are we asked to find here? We are asked to find the mass of unreacted iron. First, we have to take note of our parameters given in the question. The question told us that volume of hydrogen tetraisosulfate 6 reacted in the equation to be 5. The volume is 10 centimeter cube. And the molar concentration of this same hydrogen tetraisosulfate 6 from this, we can easily find our mass. From this, we can easily find our number of moles of hydrogen tetraisosulfate 6. The formula to find the number of moles, which we represent as small letter n, is equals to molar concentration, which is our molar concentration, which is our concentration in mole per dm cube, times volume, which is in cm cube over 1000. Now we are dividing it by 1000 because our volume is in centimeter cube, and hence we have to convert it to dm cube so it will align with our molar concentration. Now, by imputing our values, we have 1.0 times 10 divided by 1000. This will give us 0.01 mole. Now, we know our number of moles of hydrogen tetraisosulfate 6 that reacted. And from this equation, the mole ratio here shows that 1 mole of iron reacts with 1 mole of H2SO4, which is hydrogen tetraisosulfate 6. And already, we know that 0.1 mole of hydrogen tetraisosulfate 6 reacted in this question. So automatically, if 1 mole of this reacts with 1 mole of this, 0.01 mole of this will also react with 0.01 mole of iron. So if 1 mole, according to our reaction, 1 mole of H2SO4 reacts with 1 mole of iron and 0.01 mole of H2SO4. So if 1 mole of H2SO4 reacts with 1 mole of iron, 0.01 mole of H2SO4 will automatically react with 0.01 mole of iron. So now we know that the number of moles of iron that reacted in this equation is 0.01 mole. But the question asked us to find the mass of unreacted iron. To find our mass, the formula we use is to find our mass, we'll use the formula number of moles times molar mass. Now, the number of moles we've discovered to be 0.01 mole, and our molar mass was given in the question, which is 56. 0.01 times 56 will give us 0.56 grams. But this is the mass of reacted iron, or the mass of iron that reacted. But the question asked us to find the mass of iron that did not react, the unreacted mass. To do this, we'll have to subtract this from the total mass of iron given in the question, which is 5.0 grams. So to find the mass of unreacted iron, the mass of unreacted iron, we'll subtract the mass of reacted iron from the total mass, which is 5.0. So 5.0 minus 0.56, this will give us 4.44 grams. Therefore, the mass of unreacted iron is equals 4.44 grams. So this is our final answer. Now we'll be looking at the next question. Our next question is taken from question year 2018, question 4B. 4BI says state Dalton's law of partial pressure. Dalton's law of partial pressure states that in a mixture of gases which do not react chemically together, a gas will exert a partial pressure, which is the pressure it will exert if it is kept alone. II reads, the volume of a sample of methane collected over water at a temperature of 12 degrees Celsius and a pressure of 700 mm mercury was 30 centimeter cube. Calculate the volume of the dry gas at STP. Saturated vapor pressure of water at 12 degrees Celsius is 10 mm mercury. Now, we have to take note of our parameters. We have our T1, which is temperature, to be 12 degrees Celsius. But you know, when calculating questions of this type, which are under gas laws, we convert the degree centigrade, to Kelvin. Converting to Kelvin, the formula is degrees Celsius plus 273. This will give us 12 plus 273. So we have T1 to be 285 Kelvin. Now, our volume, V1, was given as 30 centimeter cube. And our P1, the pressure stated there was 700 millimeter mercury, but that was because methane was collected over water. And the saturated vapor pressure of water given in the question was 10 millimeter mercury. To get our P1, we have to subtract the 10 from 700. This will give us 690 millimeter mercury. Hence, our P1 is 690 millimeter mercury. The question asks us to calculate the volume at STP. This means our V2 is unknown. This means our V2 is unknown, but our T2 and P2 were not given, but they were given because it stated that calculate the volume at STP. And we know that at standard temperature and pressure, the standard value for temperature is given as 700, and the standard value of temperature is given as 273 Kelvin, which is 0 degrees Celsius. And the pressure at STP is 760 millimeter mercury. So since we have our values, initial volume, which is V1, T1, P1, V2, T2, P2. This is in alignment with the general gas equation, which is V1, P1 over T1 equals to V2, P2 over T2. By imputing our values, we'll have our V1 is 30 times P1, which is 690, is equals to V2, which is our unknown value, times 760 divided by T1, which is 285, and here we have T2, which is 273. Now we'll make V2 our subject of formula, and by doing that we have to cross multiply. Hence we have V2 is equals to, cross multiplying this by this, 30 times 690 times 273 divided by 285 and this. Now 30 times 690 times 273, please calculate that. This will give us 5,651,100 divided by 285 times 760, which will give us 216,600. This divided by this will give us 26.09. If you calculate it, you see it. This is volume. Hence, our V2 or our volume at STP is given as 26.09 centimeter cube. Now, it is very important that you show each step taken so that your examiner understands or knows that you understand what you are doing. I hope you understand. Let's look at our next question. Our next question will be taken from the year 2017, question number 1J. And this question reads, write the electron configuration of 26Fe3+. Now this Fe represents ion, and 26 here represents the atomic number of ion. First, before we write this, let us write the electron configuration for ion. Now, before we fill the electron configuration of this, we'll first write out the electron configuration of ion without this 3+, which is 1s2, 2s2, from this. 1s will be written first, like that. Next is 2p6, and we have 3s2. This is, if we want to know if it corresponds, we can easily count the number of electrons on top to make sure it reaches 26. So here we have 4 plus 6, 10, plus 2, 12. We still have 14 more to go. Here we have 2 plus 2, 4, 10, 12, 18, 20. So 3D always takes 6. So the electron configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. But usually when writing the electron configuration of iron, we write 3d6 first, but this can also fly. But the reason why sometimes 3d6 is written first is because the electrons in 4s will easily be lost because it's just 2 electrons that are filling the s block. So to fill the electron configuration for this, which is given in the question, this 3 plus represents that iron is losing or has lost or can lose 3 electrons. And with what I explained earlier, 4s, the electrons in 4s will easily be lost first. Then 1 electron will be lost from the 3d block orbital. So to fill this, we have 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5. 26 minus 3 is 23 electrons. So a total of this is supposed to be 23 electrons. So this 4 plus 6, 10, plus 2, 12, plus 6, 8, which is 18. 18 plus 5 will give us 23. Hence, this is the electron configuration for 26Fe3+. That's all we'll be taking for today's Passnownow's WAEC preparatory class on chemistry. You can always go back and solve questions of similar structures to familiarize yourself with such questions. Thank you for staying with me. Bye-bye.